Since we've talked about combustion reactions, I do want to talk about combustion analysis, because combustion analysis allows us to determine percent composition of different atoms inside any different compound. Okay? So I'm going to start with this molecule, near and dear to all of our hearts. That's ethanol. Okay? When I burn ethanol, I do combustion analysis, I got to use oxygen, and I'd be generating carbon dioxide and water. Okay? Now, a lot of times when we burn these things, what we're determining is how much carbon and how much hydrogen are each of them. But before I do that, I'm going to balance this reaction. So I want you guys to pause this, and then we're going to go ahead and balance it. So I want to see if you guys are correct. Okay, so pause. All right, now we're going to go ahead and try to balance this thing. All right? So I'm going to write the atoms on either side. C2, okay, H6. And I've got one oxygen plus 2 over here with the oxygen. The carbon dioxide, I've got one carbon, all right? I've got an oxygen down here, it's 2. I've got a hydrogen, that's 2 plus 1 oxygen, okay? So I'm going to make sure that my carbons line up. So I'm going to put a 2 in front of the carbon dioxide and then work to balance from there. Okay, I put a 2 here and put a carbon dioxide. That's a 2. Okay, I got to multiply my oxygens at that point. This becomes 4. Okay, now my carbons are balanced on either side. I've got to balance out my hydrogens. So I'm going to put a 3 here in front of H2O. So now that brings me to 6, and that brings me to 3. I've got 7 on that side. So that's not going to even out here with the oxygen. So what do? That's right, you multiply everything by 2. That's 4, 12. Now I've got 2 oxygens. All right, I'm going to change this to 4 and this to 6. 4, change that one to 8, and this one goes to 12. And now I've got 6 more hydrogens. So I've got 14 hydrogens in total, or excuse me, oxygens in total there. So what number do I need? Is 7 here. Good. All right. So hopefully that's the answer you got for the combustion of glucose. Again, not glucose, excuse me, ethanol. And now what we're going to do is we want to look at what happens in a combustion analysis. When we blow up ethanol, we analyze it to find its mass percentage. It's called elemental analysis. So let's see how that's done. All right, so what I have here, this is a combustion analysis material, or as a chamber. And what I do is I put my sample here, and then I burn my sample under extreme heat. We're talking 700 degrees Celsius. So the sample inside vaporizes, but it only vaporizes in the presence of pure oxygen. Okay? So you have sample here, plus oxygen gas. That's where that oxygen comes from, okay? So that's the oxygen, and the sample is right here. So when that burns, it's going to pass through a couple of filters. The first filter that's here is copper oxide. That just ensures that all carbon is turned into carbon dioxide, okay? The second filter that we use is used to capture carbon dioxide, all right? So we know what the original mass of that filter is. As it absorbs carbon dioxide, it's going to increase in mass. The second filter is designed to capture water. All right? Notice that none of these filters capture oxygen because we had to add oxygen into the chamber. So once we add that oxygen, we have no idea how much oxygen we've added. Okay? We have infinite oxygen at this point. But we do know how much carbon was captured, and we do know how much hydrogen was captured. So when we look at these things in combustion analysis, we weigh it versus the sample weight, we're able to determine how much percent of that sample is carbon and how much of that percent is going to be hydrogen. Okay, and what this gives us, if you remember way back to our earlier discussions, this is about mass percentage. Okay, so when we combust this thing, right, carbon is how much of ethanol? Well, this goes 12. So if we look at this, this is 12.011 times 2 divided by 12.011 times 2 plus 1.0079 times 6 plus 16.00. That's the mass of this thing. All of these things are in grams, all right? But the grams themselves are going to cancel out. So what this is going to give us is this is going to give us a certain percent of the mass that is going to be carbon, all right? So my mass percent, when I weigh this thing out, is going to give me the percentage of carbon that I have in the sample. And I'll do some math here. All right, so ethanol weighs 46.0694. We do the math there. And this top one's equal to 24.022. Okay, divide both of those, you'll lose grams, and what you are left with is a mass percent of 52%. Okay, so the mass percent that we're going to get of carbon here is going to be 52%. Now, the mass that we're absorbing is carbon dioxide, so we have to be aware of that. Okay, so the mass of carbon that we're getting from the sample is going to be actually a percentage with the carbon dioxide. Okay, so you got to weigh the carbon dioxide weight, which is about 44, to get an idea of how much carbon is in the sample. Same thing with water. When we burn the hydrogens, it's making water. Water is being absorbed in a filter. We weigh that filter and determine how much hydrogen was released by the sample. How much oxygen is there? We have no idea from these measurements, but we can figure it out from what's left. Because once we get the percent composition that is hydrogen and carbon, we'll be able to figure out what the percent composition of hydrogen is. And hydrogen in the sample is 1.0079 times 6. Okay? So we're going to use the same equation essentially, but in this time we're going to write 6.0474 grams on the top instead of the 24.022. And our mass percentage is going to be 13.13. Okay, so this one comes out to about 13%. So if this is 52 plus 13 is going to give us 65. That means 35% of the sample that's left over is going to be the oxygen weight. Okay? That's how we figure those things out. Now it should be noted, whenever I do this combustion analysis, I'm going to get a sample that is empirical. So the formula that I'm going to get here is going to be empirical. So when I look at the ratios that I've got here of carbon, hydrogen to oxygen, I'm going to have a 2 to 6 to 1 ratio. Okay? So my formula could be 2 carbons, 6 hydrogens, and an oxygen, that's just 1. Or I could have C4, H12O2, or C3, H18O3. All of those things are possible in this case. Okay? It only gives us empirical formula, not exact molecular formula.